Thank you very much. Yeah, so this is a joint work with Maris Ozols. And the plan for my talk is as follows. So first I will introduce the motivating problem, which our journey started from. Then, in order to solve it, and so first I generalize it, and then in order to solve it, I would need to introduce one technical ingredient called the Brauer algebra. Then I would also need to explain the mixed Schur-Weyl duality. So after that, I will be able to state our main results, and I'll talk a bit about the applications of the framework which we developed. So consider the following problem. So let's say you have a Boolean majority function for concreteness on 3 inputs here. So one thing you can observe about this Boolean function is this is equivariant function, meaning that if you negate all the input all the input bits, the output will be also negated. And we want to ask the following question now. Can we somehow realize this Boolean function as a quantum channel? And what do I mean by this? I mean the channel which would basically would take as input the product states, and the states would come from some orthonormal basis. And this channel would need to output the majority state. And this, on top of that, this should work for every choice of the basis. And implementing this channel idealistically is impossible. It's not a very difficult argument, so you just need to look at the Stein-Spring dilation of this channel, and you would get a contradiction to the linearity, much like in the style of non-cloning theorem. So now, this ideal map is impossible, but how well we can quantumly approximate this ideal map? Well, in order to do this, we would need to solve the following semi-definite program. So here, I want to maximize the worst-case fidelity, and here I want to consider all possible input strings obtained in the arbitrary basis, and I basically want to compute the fidelity with an ideal output. And this particular problem, when you consider qubits and only one output, basically like the Boolean functions, was already solved by previous work, and you can watch the talk by Maris Ozols at QIP2023 on this. But we want to go further, and I want to ask a question about general channels with general inputs and outputs. So we want to consider an arbitrary channels where the local dimension of the system is D, and we have P inputs and Q outputs. So this would be our parameters, P, Q, and D. In order to solve the optimization, we would look at the Schur matrix of the channel. So the Schur matrix is essentially defined as follows. So you just need to take all the elementary matrices which form a basis of the space of the matrix space, and you need to act with the channel in this basis. So this encodes as much information as in the channel, and the usual definition of complete positivity translates into the positive semi-definiteness of this matrix X, and trace preservation is some partial trace constraint. And we want to look at specific channels which are unitary-equivariant, as in this toy modeling problem on quantum majority. Namely, we apply a local unitary on the input, it will translate to applying the same unitary on the outputs. The same condition in terms of the Schur matrix will be the following commutation of the Schur matrix X with this tensor product of the unitary. So here you have the unitary to the tensor power P, unitary conjugate to the tensor power Q. So, and the general question is, can we optimize over such set of channels? So more formally, we want to consider the general SDP, which has this general form. So yeah, we have some linear objective here, some positive semi-definite constraints, some linear constraints, partial trace constraints, and this symmetry constraint. So this matrix, if you would want to solve this naively, this matrix has the size d to the power p plus q times d to the power p plus q, and kind of infinitely many constraints you have, right? So this is true for every unitary. So, and for example, if you take modest numbers like for 1 and 10 for PQD, you'd get 10 to the 10 variables. So just to put this into the context, such in SDP, you may encounter in the following quantum information problems. So like quantum state purification and cloning, port-based, multi-port-based teleportation, entanglement detection. This is just some subset of examples, of course. And now, in order to utilize the symmetry property, we essentially want to ask the question how we can describe the commutant of this mixed tensor unitary action. So this brings me to the Schur-Weyl duality. So for the beginning, let's assume that we don't have an output system, the case Q equals 0. And in order to explain this, I would need to introduce a couple of notation. So this curly U is the matrix algebra, which is spanned by the products of these unitaries to the tensor power P. And I would need to define another algebra, which comes from the symmetric group. So essentially, this CSP is the group algebra of the symmetric group. And then you want to think about this group algebra not abstractly, but as in terms of matrices. And this map psi would map these permutations to matrices in the following manner. Just permute the registers. So you can think about this psi map as being a natural tensor representation of the group of the symmetric group algebra. And finally, we need to introduce the notion of centralizer of the algebra A. So this is the set of matrices from the space of all matrices, which would commute with all the matrices from our algebra A. And then the Schur-Weyl duality is the classic result in representation theory, essentially states that this algebra U is the centralizer of the algebra A and vice versa. And moreover, when local dimension is big enough, this representation is faithful, meaning that you actually have isomorphism between this matrix algebra A and this kind of abstract group algebra. So now what about the case Q greater than 0? So in order to explain that, I would need to introduce the Brauer algebra. So one way to define it is to look at the permutations diagrammatically. So let's say we have this permutation, and then what you would need to do, you would need to take the last Q systems and flip them. You would get the diagram like this. So there would be like a wall here. This is where this vault comes from. And you would have instead of vertical strands, you may also have horizontal strands, which will go through this wall. And it's easy to see because of kind of this mapping that this dimension of this algebra is exactly the same as the dimension of symmetric group algebra, which is P plus Q factorial. And the multiplication in this algebra is defined as follows. So you just take two diagrams, sigma 1, sigma 2, you concatenate them. And in the process, some loops may appear, and you would just erase, you would need to count them, you erase them, and then you put this dimension factor d to the power of the number of loops. So this is a multiplication in this algebra. So now, how we can think about these diagrams in terms of matrices. So I want to explain how we define this psi map now from this Brauer algebra to matrices. So the usual transpositions, they are defined pretty naturally, right? So this would be just a swap matrix. So if you have a like horizontal strands, like horizontal diagram like this, which we call a contraction, this is essentially corresponds to the normalized TPR state. And for the general diagram, if you want to represent it as a matrix, you can compute its matrix entry as follows. So you basically take the coordinates of the cat, you put them at the bottom, coordinates of the bra, you put at the top, and then you just need to put the Kronecker deltas. And then in this way, you compute the matrix entry. It's very easy to compute traces if you have a diagram like this. So what you need to do, you just need to connect the opposite vertices and just count the number of loops and raise d to this number. Raise d to the power of this number. Yeah, so this brings me to the mixed Schur-Weyl duality. So essentially, pretty similar statement as the original one, but now we have a bit different algebras. So now the algebra U is spanned by this mixed tensor unitary powers. The algebra A is basically the image of the Wald-Brauer algebra under this psi map. And the statement is that the U is a centralizer of the algebra A and vice versa. And also, when local dimension is big enough, this representation is faithful, meaning that you can really think about this matrix algebra as being isomorphic to the Wald-Brauer algebra. Yeah, so we recover the original Schur-Weyl duality if we fit Q equals 0, P equals 0. So to summarize, we can say that the following are equivalent, that if we have a unitary equivariant channel phi, this is equivalent to say that its Choy matrix commutes with all the unitaries of this form. This is equivalent that the matrix X can be written as a linear product of these diagrams, and then you would map them under this psi map. But it's easy to see that you can view it a bit differently. So you can say that there exists a change of basis, which is called the Schur transform, such that if you apply it to your matrix, the matrix will block diagonalize, and the blocks will be essentially labeled by the irreducible representations of the algebra A. And you would have two registers here. So one register would correspond to the Wald-Brauer algebra. So I denoted by X lambda. And the other register would correspond to the unitary part. And in this case, because you have this unitary symmetry, you would have an identity matrix here. So you see that the number of variables has reduced drastically in order to describe the matrix X, which has this symmetry. And a key insight here is that if we impose even additional discrete symmetry on this blocks X lambda may become diagonal. And in our applications, they become diagonal in the so-called Gelfand-Zetlin basis. I would not have time to properly explain how this basis is defined. For the purposes of the talk, you should think about this basis as being some kind of very specific canonical basis. And now, essentially, the main problem is, can we write the ansatz for our matrix X, which wouldn't use the Schur transform, because the Schur transform scales badly, especially in terms of the it has a dependency on the local dimension D. So can we basically find a way to write an ansatz for X, which automatically ensures that X lambdas are diagonal in this Gelfand-Zetlin basis? So this brings me to our results. So we can do this. So we can obtain the exhaustive ansatz for our matrix X, which ensures that these blocks X lambda are diagonal in this basis. And so this is essentially written like this. So it's just a linear combination of some projectors, which we call epsilon t. In the representation theoretic language, these are called primitive idempotents. But you just can think about them as being orthogonal projectors onto the diagonal entries of these blocks X lambda. And we find these idempotents completely diagrammatically. So we essentially can write them as a sum of these diagrams from the Wald-Brauer algebra. So this ansatz is nice, and it can be used if you have, for example, some additional symmetry, in particular if you have a permutational symmetry. So if you remember, I started with a majority function. So for the majority function, you can permute the inputs. So here, if we use the symmetry, if we impose the symmetry, then we can use the ansatz. And in particular, for technical reasons, we would require that there is minimum between P and Q is 1. But moreover, we're actually able to show that the SDP can also be reduced to linear program under this symmetry if you have IZD equal to 2 or at most 2 systems. The minimal number of input-output systems is at most 2. So the main result more formally looks like this. So recall we had this SDP. And now, assuming an additional discrete symmetry, we can simplify this SDP, essentially rewrite this to an equivalent linear program, which has much less number of variables than the big N. So the big N is like the main parameter here, which is essentially the dimension of the Wald-Brauer algebra, which is P plus Q factorial, and this number of constraints. So you see that the dependence on local dimension is completely gone. And for example, if you take our initial parameters, example of parameters with 4, 1, and 10, we're essentially able to reduce from this number of variables to this number of variables. And what we can also do with this, by knowing this primitive idempotence, these projectors, we're actually able to compute off-diagonal entries of the blocks as well. But in this particular paper, this is more like a heuristic result. And this doesn't scale very well in terms of the computational complexity at the moment. So this brings me to the applications. So the first application is to find the quantum majority vote channel. And let's say we want to look at the local dimension 3 here. So remember that we had this optimization problem. So we can use our framework to essentially reduce it to a linear program, and then we can solve it for arbitrary local dimension. And it turns out that for arbitrary local dimension, we would have a worst case fidelity equal to 8/9. Another application is a problem of transformation of the black box unitary. So in this problem, imagine that you are given n copies of unknown unitary u, and you want to transform it into some function of this given unitary. In particular, here we focus on the transposing the unitary. So another way you can think about this is that you have a super channel, which essentially a map which maps channels to channels. And in order to solve this problem, when you formulate, you will formulate it as an SDP, and it turns out that the matrix variable for which you optimize essentially have this symmetry. And this falls perfectly into our framework, and we are able to utilize this to actually find some particular numbers for the channel fidelities of this problem, and we find a very nice result that actually, for the case of qubits, you need only 4 copies to implement this thing deterministically and exactly. A similar result was actually also recently obtained, but for a different function, for the inverse of the unitary by the work by Yoshida, Soeda, Murao. So, and this brings me to the final application, which is asymmetric cloning. So in this problem, we want to find a channel which maps one input system to the Q output systems, such that it kind of clones the given state rho. What do I mean by this? By this I mean that the marginals of this channel would essentially produce you this kind of noisy version of the original state, and you want to make these probabilities in this mixture as big as possible. So there was a recent work on this by Nikita, Pellegrini, and Rochette in 21, and we are able to use our framework to extend their results. But also, actually quite recently, they managed to resolve this fully analytically, which is a nice thing. And yeah, just to show you that using our framework, we were able to obtain pictures like this. Basically, these are the allowed regions for these probabilities for these marginal channels, for this asymmetric cloning problem. So I just give you a couple of applications. There are many more, and I encourage you to find them and maybe use our framework. So, and the open problems we have so far are as follows. So I mentioned that we have a kind of a heuristic approach to extract of diagonal entries of these x lambdas, and this is actually like a work in progress to rigorously justify this. Another problem is actually once we have a solution of this matrix X as a linear combination of diagrams, we want to find an efficient quantum circuit which actually implements it. So I must say that there exist works which transform given Choi matrices or Stein-Spring representation into quantum circuits. But here I'm specifically asking for this problem that if we know this, that the X is a linear combination of the diagrams, can we somehow use this to find these decompositions even more efficiently. Another problem is to characterize the kernel of the map psi. This is more like a technical problem because if you can solve this, then this can provide an additional massive speedups when the local dimension is small. Another one is to derive an explicit basis for this particular permutational symmetry. So we know that in this case the SDP would reduce, but unfortunately we don't know the exact basis yet. And the last one is to extend our method to other algebras and to other problems in quantum information. So with that, I want to thank you for your attention.
Thank you. Very well. Does anybody have any question? Yep.
Hello, thank you for a nice talk. Could you go back to this problem of unitary transposition? So first question is, you solve it for parallel scheme, right?
No, sequential.
Sequential.
This is sequential, yeah. So for parallel, you cannot achieve this, I think. So this means that there exists a deterministic and exact, essentially, protocol. Yeah.
But if you have sequential, how you can impose this symmetry, SP times SQ?
Yes. So, well, yeah, I was very quick over this. So I didn't impose this SP times SQ symmetry in that case. I just used the unitary equivariant symmetry. So in that case, it was an SDP. And I mentioned that knowing the primitive idempotence, we can actually use them to write these blocks fully. So we can also solve the SDP. But current methods are kind of heuristic. And yeah, so we are working on actually putting this on paper to prove this rigorously that it works.
And this is only for d equal to 2, right? You have?
Yes, exactly. So, for example, for d equal 3, the problem becomes really big, and like on my laptop, I cannot really.
For qubits, you know that you don't have to use Brauer algebra to solve it, right? Because then it's completely you can translate it to normal Schur-Weyl duality. U bar is you can conjugate U bar by one of the Pauli matrix to obtain.
Yes, I agree that you can use this maybe simpler framework, but yeah, the point is that you can also generalize it right to qubits if you want. And
yes, of course.
Yeah.
Yes. Okay, thank you very much.
Yeah.
Yeah, thank you for the very nice talk. Yeah, my question goes in a similar direction. So when number of copies are equal, then you should also be able to reduce it to usual Schur-Weyl duality. Can you explain how one can see that in the diagrams?
Sorry, which?
The P and the Q, I believe.
When they're the same.
When they're the same, yeah. And everything should simplify. Is that right?
Yes, I think you're right. It should simplify, but yeah, immediately from the top of my head, I cannot really tell you how exactly.
Thank you.
Sorry.
Yep.
Thank you for a nice talk. For your open program in the last slide, you mentioned about efficient implementation of the circuit, right?
Yeah.
And for P equals 0 case, then you can use a quantum Schur transform to implement that circuit, right? So do you expect more efficient circuit than using the quantum Schur transform, or?
Well, so yeah, so here I really mean that because in general you might have a lot of input and a lot of output systems. So in that case, I wouldn't. So yeah, if you have only one output system, yes, I understand that you can use maybe the Schur transform and derive kind of the primitives from the Schur transform. Yeah, but for more outputs, I don't really know actually how one should think about it. So here I'm just really thinking in terms of, okay, I have the matrix. I know that it's kind of a linear combination of diagrams. Maybe, each individual diagram has a certain physical meaning and you can implement it efficiently. And I'm asking basically how you can utilize this knowledge to compile the circuits and find them faster, yeah.
Okay, thank you.
Any other question? Oh, yes.
Yeah, thanks for the talk. So I was wondering, like, in your motivating question, you talk about this majority vote, and if you allow for some ancillas, maybe then you can solve it exactly. So, like, is there a way for your framework to deal with ancillas? Like, can you still write an SDP and have some kind of representation theory to, to solve that?
Yeah, it's a nice question. Yeah, actually, I haven't thought about this. Yeah, I don't really know, but I can imagine that still, on the register where kind of without ancillas, you would have some kind of symmetries, right? So I'm pretty sure you can still use the framework, but yeah, I'm not sure how efficient it would be in that case. Yeah,
Okay,
so.
thanks.